In this video, we'll take you inside the supergiant gold mines of the world, where millions of tons of rock are blasted, hauled, crushed, and refined, all to produce just a few shiny bars of one of Earth's most valuable metals. From the blasting of rock to the smelting of pure bullion, this is the jaw-dropping journey of gold. Before we dive in, don't forget to like this video, subscribe, and hit the bell icon, so you never miss our deep dive documentaries into how the world's most valuable resources are made. Gold has fascinated humanity for thousands of years. Ancient civilizations like the Egyptians, the Romans, and the Incas treasured it not only for its beauty, but also for its rarity. Gold doesn't rust, doesn't tarnish, and its luster lasts forever. This permanence gave it a mystical quality, making it a symbol of wealth, power, and eternity. Today, gold remains essential, not just for jewelry, but for technology, finance, and even medicine. It's used in smartphones, satellites, and life-saving medical devices. But despite our modern world, one thing hasn't changed. Extracting gold is incredibly difficult. To produce a single ounce of pure gold, miners often need to process over 30 tons of rock. This insane ratio is what makes gold so valuable. And in supergiant mines, where entire mountains are reshaped, the process is on a scale that's almost unimaginable. So how do we go from raw stone buried deep underground to a shining gold bar locked away in vaults? Let's step inside the world of giant gold mining. The journey begins long before the first shovel of dirt is moved. Mining companies spend years, even decades, just looking for the right place to dig. Geologists search for areas with signs of gold deposits. Sometimes it's rivers with tiny gold flakes, sometimes it's rock layers that hint at ancient volcanic activity. And sometimes it's old mining sites that still hold untapped potential. They drill exploratory holes hundreds of feet deep, bringing up rock samples. If lab tests confirm the presence of gold in significant amounts, the mining project moves forward. Gold is rarely found as nuggets. Instead, it's trapped inside hard rock. To get it, miners must remove entire layers of earth. At supergiant open-pit mines, the process starts with controlled explosions. Engineers drill massive holes into the rock, carefully pack them with explosives, and detonate them in a sequence. A thunderous blast shakes the earth, breaking apart millions of tons of stone. After blasting, the heavy machinery moves in. And when we say heavy, we mean it. Gigantic haul trucks the size of two-story houses rumble through the mine. Each truck can carry 400 tons of rock in a single load. Excavators with buckets larger than cars scoop up the blasted rubble and load it into these trucks. The operation runs 24/7. Day and night, fleets of trucks move back and forth, transporting raw rock to the crushers. From above, the mine looks like a vast staircase spiraling into the earth, each step representing millions of years of geology being peeled away by human hands. It's staggering to think that most of this rock is just waste. Only a small fraction contains gold. That means for every gold bar produced, mountains of leftover rock, called tailings, are piled up around the mine. Next comes grinding. Massive rotating mills, filled with steel balls, tumble the crushed rock until it becomes a fine powder. Imagine turning a boulder into dust. That's what these mills do, often processing hundreds of tons every hour. This powder is then mixed with water, creating a slurry. Now the gold is still locked inside, but the slurry is ready for the next stage, chemical separation. It's here that gold mining moves from brute force to precision science. Gold doesn't separate easily. To pull it out, miners use chemistry. The most common method is cyanidation. The slurry of powdered rock is mixed with a cyanide solution, which dissolves the gold, separating it from the worthless rock. While cyanide sounds dangerous, and it is, mining plants operate under strict safety systems to prevent leaks and contamination. Another technique is flotation, where air bubbles are pumped into the slurry. The gold particles attach to the bubbles and float to the surface, where they're skimmed off. After separation, the gold-rich solution is passed through activated carbon or zinc precipitation, pulling out the gold from the liquid. What's left is a concentrated material, still not shiny yet, but much closer to pure metal. This process is carefully monitored with labs inside the plant. Every hour, technicians test samples to ensure maximum recovery. After all, every tiny speck of gold is worth money. By this point, millions of tons of rock have been reduced to just a few pounds of concentrate. But it's still not the beautiful gold you imagine. To get that, we need fire. The final transformation happens in the smelter. The gold concentrate is dried and placed in furnaces, reaching temperatures of over 1,100 degrees, 2,000 degrees Fahrenheit. At this heat, the gold melts, separating from impurities like silica, iron, and sulfur. These unwanted materials float on top as a molten slag, which is skimmed away. What's left is glowing liquid gold. Workers carefully pour it into molds, where it cools and solidifies into doré bars. These bars aren't perfectly pure, usually around 80 to 90% gold, but they're ready to be shipped to refineries. At the refinery, advanced processes like electrolysis bring purity up to 99.99%. The final product? Perfectly polished gold bars stamped with their weight and purity. The kind you see stacked in bank vaults or traded in global markets. Think about it. A journey that started with millions of tons of rock has ended in just a handful of shiny bars. This contrast, from sheer volume to extreme rarity, is why gold holds its value so powerfully. If you enjoyed this journey inside the hidden world of mining, make sure to hit that like button, subscribe, and tap the notification bell, so you'll never miss our next exploration into the industries that power our world. Thanks for watching, and we'll see you in the next adventure. From the smartphones in our pockets, to the wiring that keeps our homes bright, and even the engines that drive our cars forward, copper is everywhere. It is one of the most essential metals on Earth, and yet, very few people know exactly how it's pulled from deep within the ground and turned into shiny, pure copper that powers our modern world. Thousands of meters below the Earth's surface lies a vast treasure chest of copper ore. But unlocking that treasure isn't as simple as digging with a shovel. It's a process that requires giant machines, explosive force, precision chemistry, and weeks, sometimes months of transformation before a rock can become one of the world's most useful metals. Today we're taking you inside that journey. From exploration and blasting, to crushing, smelting, and refining. This is the mind-blowing story of how copper is mined, processed, and made ready for the world. But before we dive in, don't forget to hit subscribe, tap the notification bell, and give this video a thumbs up. Trust me, you don't want to miss what's coming next. Copper is often called man's first metal. Why? Because it was one of the very first metals ever used by humans, dating back more than 10,000 years. Ancient civilizations like the Egyptians and Mesopotamians discovered that copper wasn't just shiny and beautiful. It was also strong, malleable, and resistant to corrosion. That meant it could be shaped into tools, weapons, jewelry, and even the very first plumbing pipes. Fast forward thousands of years, and copper remains just as important, if not more. Today, copper is the backbone of modern technology. It conducts electricity better than almost any other common metal, making it essential for power lines, motors, electronics, and renewable energy systems like wind turbines and solar panels. Without copper, much of the modern world would literally go dark. In fact, copper demand is skyrocketing. With electric vehicles, green energy, and global electrification, the world now consumes over 20 million tons of copper every single year. And where does all that copper come from? Not from recycling alone, though recycling is hugely important, but mostly from mining deep deposits hidden inside the earth. These deposits aren't pure copper metal. Instead, they're ores, rocks that contain copper minerals like chalcopyrite, bornite, and malachite. Typically, copper ores only contain a small percentage of actual copper, often less than 1%. That means for every ton of copper extracted, miners must move and process hundreds of tons of rock. This is where the journey begins. Locating those deposits, digging massive mines, and then transforming ordinary rock into one of the most valuable metals on Earth. So, how do we actually find copper in the first place? The Earth's crust contains copper scattered almost everywhere, but only certain locations have concentrations high enough to be mined profitably. That's where exploration geology comes in. Geologists begin by surveying landscapes using satellite imagery, mapping rock formations, and analyzing soil chemistry. They look for signs of copper minerals on the surface, greenish stains of malachite, or bluish hints of azurite. But since the richest deposits often lie deep underground, scientists rely on advanced tools like magnetic surveys, seismic studies, and drilling core samples. When drilling, a cylindrical piece of rock is pulled out of the ground, often hundreds of meters deep. Geologists examine these cores to estimate the size, depth, and grade of a copper deposit. If the results are promising, companies spend years and millions of dollars conducting feasibility studies. They ask questions like, how much copper is really here? How much rock must be moved? What's the environmental impact? Can this mine be profitable for decades? Once approved, it's time to dig. And depending on the deposit, miners use two main methods: open pit mining and underground mining. The journey starts at the primary crusher. Here, gigantic rocks, sometimes the size of a refrigerator, are dumped into a machine with steel jaws. These jaws slam together with immense force, reducing boulders into fist-sized chunks. The process doesn't stop there. Secondary and tertiary crushers further reduce the pieces down to gravel-like sizes. Why so small? Because the smaller the particles, the easier it is to free copper minerals from the surrounding rock. After crushing, the ore heads to the grinding mills. Imagine enormous drums, each bigger than a bus, rotating day and night. Inside, steel balls or rods tumble with the crushed ore. As the drum spins, the heavy balls crush the ore into a fine powder. At this stage, it looks less like rock and more like wet sand or even muddy slurry. This fine grinding is crucial because copper minerals are often locked within the tiniest grains of rock. Now comes the ingenious part: separating valuable copper minerals from waste rock. Since copper minerals often have unique surface properties, miners use a method called froth flotation. This step is magical when you think about it. Out of tons of dull gray rock, we've now isolated a small but powerful concentrate brimming with copper minerals. But we're not done yet. The concentrate still contains sulfur and other impurities, so it needs to be transformed into pure, usable metal. At this stage, enormous conveyor belts and pipelines move the copper concentrate to smelters or processing plants. From muddy slurry, the journey is about to leap into the world of fire, heat, and chemistry. After concentration, the copper-rich slurry, now upgraded to about 30% copper, travels to one of the most dramatic stages in metallurgy: smelting and refining. This is where chemistry, heat, and human ingenuity combine to transform dull concentrate into glowing, usable copper metal. The concentrate, still containing sulfur and iron, is dried and fed into huge furnaces. Imagine steel chambers large enough to hold a small house, burning at over 1200 degrees Celsius to 200 degrees Fahrenheit. The molten matte is then transferred to another furnace called a converter. Here, air or pure oxygen is blasted through the molten material. The oxygen reacts with the remaining sulfur and iron, driving them out as gas or slag. The result, a product called blister copper, so named because its surface appears blistered with bubbles of escaping gas. This blister copper is about 98 to 99% pure. But 98% isn't good enough for modern technology. Smartphones, electrical wiring, and medical devices demand ultra-pure copper, 99.99% purity. To reach this perfection, blister copper undergoes electrolytic refining. When the process is complete, what emerges are sheets of copper so pure they gleam like mirrors, ready to be rolled, drawn, and manufactured into countless applications. From ore dug deep in the earth, we've now produced one of the world's most essential materials. The copper you see in wires, plumbing, cars, electronics, even renewable energy systems like wind turbines and solar panels, all trace their origins back to this fiery transformation in smelters and refineries. If you've enjoyed this journey into the hidden world beneath our feet, imagine how many more stories the Earth is waiting to tell us. Subscribe to the channel, hit that notification bell, and join me as we uncover more secrets of science, nature, and the incredible materials that shape our modern life. Don't just watch, be part of the adventure. Beneath the Earth's crust, hidden in ancient volcanic formations, lie some of the most prized treasures known to mankind. Diamonds. For centuries, these shimmering stones have captivated royalty, industries, and investors alike. But their story begins long before they ever reach a jeweler's display. The history of diamond mining stretches back over 2,500 years to ancient India, the first known source of diamonds. These early gems were found in riverbeds and traded along the Silk Road, believed to bring strength, invincibility, and spiritual clarity. By the 18th century, Brazil had become the world's largest supplier, before the discovery of massive deposits in South Africa changed everything. In 1867, a young boy found a shiny stone along the Orange River, a 21-carat diamond that sparked a modern diamond rush. This led to the founding of some of the world's most famous mines, including Kimberley, home to the legendary Big Hole. Today, diamond mining is a high-tech global enterprise. The world's largest mines span across continents, from Jwaneng and Orapa in Botswana, to Mirny in Russia, Venetia in South Africa, and Diavik in Canada. Some operations reach depths of over 1,000 meters, and each year, more than 130 million carats of rough diamonds are produced globally. But how are these tiny crystals of carbon extracted from solid rock? And what does it take to bring them from the Earth's core to the world's most exclusive boutiques? Join us as we journey deep into the heart of modern diamond mining, a world of massive machines, precision science, and sparkling ambition. Geologists use satellite imaging, geophysical surveys, and soil sampling to identify promising sites. Once a potential kimberlite deposit is located, it's drilled and sampled to assess the concentration of diamonds. This process can take years and millions of dollars in investment before a mine is approved. Only a small percentage of kimberlite pipes actually contain diamonds in commercially viable quantities. If one does, the project moves into the development phase. In open-pit operations, huge amounts of overburden, layers of soil and rock, must be removed. The process begins with explosives, followed by massive hydraulic shovels and dump trucks that can carry up to 400 tons of rock at a time. This material is hauled to the primary crushing stations, where the hard kimberlite rock is broken down to manageable sizes for further processing. Once the ore is brought to the surface, it enters the primary crushing phase. Here, giant jaw crushers reduce large rocks into smaller pieces. The material is then passed through secondary and tertiary crushers to reduce it even further. By now, it resembles gravel-sized particles. The goal? To liberate the diamonds trapped within the rock matrix. From here, the crushed ore is sent into a washing and screening circuit to separate fine particles and slurries.